Hello guys, nice to see you. How are you doing? Slides. So we start actually our work on discussing our first topic, which is electricity. And let us start with some suggestions. What kind of most common electricity effects, like electricity related effects, in nature we observe very often in our everyday life? Any suggestions? Well, that is already devices designed based on our knowledge of electricity. But what happens by itself without our contribution? Lightning is that's one of the most prominent electric effect, which obviously was observed since the dawn of history. And another quite common effect, which is not so impressive, but happens quite often, and specifically under our nowadays conditions when we have very dry air inside buildings because of extremely low temperatures outside, static electricity. So we notice that quite often we touch some objects and we feel some electric shock. Very light, but could be quite annoying because it actually happens here way more often than anywhere I ever been in my life. And by the way, have you noticed that during summer, if you compare like summertime and winter time here in Astana, you feel the static electricity effect much less in summertime. So, any suggestions? What is the reason for that?
Air conductivity.
Okay, and what is air conductivity? And let's say not only air conductivity, but conductivity of all objects, like surface of all objects. What is the function of? What it depends on?
Density.
No. Like this feature which defines why during winter we experience more often the static electricity.
So I guess when it's cold, and some materials have higher conductivity, electricity conductivity. Then you call temperature.
Well, that is a bit not proper explanation because we need to add here humidity. Water vapor in the air defines how much air or other objects which are in contact with such humid air will conduct electricity. So in summertime, we have much lower, much higher humidity, relative humidity, much more moisture in air, and that allows to dissipate this electrostatic charge. However, now in winter, humidity is very low and it's very easy to accumulate electric charges, and these electrostatic effects are more often. So the thing is that it is quite difficult to build a link between lightning, which are so spectacular natural events, and these tiny electrostatic charges. So nowadays, it's quite clear that both of them have the same nature. It's electricity behind them. However, not so long time ago, like a few centuries ago, actually, it was not known. And I'm sure you have seen this guy many times, Benjamin Franklin. And you know why he's famous? Or
He kites for doing the.
Okay, yeah, that is good. We will come to that point, but that is actually not the reason why he is on this point. No? The world center of democracies and so on and so forth. Yes, so he was definitely quite active political figure in at the early stage of establishing of United States of America. However, in free time, this guy was doing weird stuff. Imagine some old guy in storm with the sky, with the kite, and yeah, that is quite interesting what he was doing. Probably people consider that he is communicating with some demons at that time, but actually he made a major contribution to our understanding of the nature of electrical processes. So, any comments on this experiment? Who can explain what's going on there?
Electricity needs to find easier way to go through.
Okay.
So the easier it is goes easier with the kite with the K than.
So let us first consider the general condition. So without this weird guy with the kite. So why it's storm time? So why do you need to do this experiment when you have a high chance of lightnings? Why you cannot come with a kite and do this experiment when you have a clear sky?
Because the negative charge builds up in the clouds.
Okay, we may not specify now negative, positive, but because of the friction between drops of water, which are in clouds, and they are pushed up with upcoming flux of air in this stormy clouds, it results in certain friction between water and air. So the friction results in electrical charging of these droplets, and as a result, clouds are also they also become electrically charged. So they are electrically charged, they create electric field. So we have, of course, all these concepts we will discuss in details, but now just general explanation. So between clouds and Earth, which is considered to be ground potential is zero, we have some potential difference between clouds and Earth, and thus in this space there exists electric field. So this electric field is quite weak, but the distance is quite big because clouds are usually very high over the ground. So now comes this explanation with the easier path. Can you continue it from this point? You have a kite, send it to the sky, and this part of the silk thread is wet because it's under the rain. So it conducts electricity quite well because of it is kind of soaked in water. So the potential up here is equal to the potential of this key, which is in contact with the part of the silk thread, which is wet, and that's why their potential should be equal. Then what our old friend Benjamin Franklin did, he just put his fingers close to the key, and being on the ground, his potential was zero, he was kind of grounded. So here you manage to create quite a large potential difference between this point, which is the same potential as here, and this point where his feet are located. So then you could see some small electric discharge, which is equivalent to what we see when these electrostatic effects are happening. When, for instance, you just take off your sweater because of friction with under the fabric, you see this electric sparks. So putting this all together, he revealed to humanity that the nature of both of these effects, lightning, which he could observe during the storm, and this electrostatic event, which happens in quite intensively in dry air. They have the same nature and they are actually electrical effects. So that was the first step in order to understand how these phenomena are connected and what is actually behind it. However, obviously, there was still a long way to go in order to understand how electricity works and eventually to design these electrical instruments which we are using nowadays. So in order to make a next step into this story, let us consider matter which surrounds us. So we consider, like we see different materials. So matter could be defined as combination of different materials. And in terms of electrical properties, what kind of materials you would distinguish?
Conductors and insulators.
Conductors and insulators. So that's very general and correct answer. And we can add here, we can maybe provide a little more information on this because what in our everyday experience associated with conductors. Obviously, these are metals because metals are the most electrically conductive materials we are dealing in everyday life. So then with insulators, that could be different. Could be plastic, which commonly used for electrical insulations of electrical instruments, wires, so on. Wood, but again, wood depends, its electrical conductivity strongly depends on humidity because if humidity increases, electrical conductivity of wood is also increases. So its ability to conduct electric charges increases also. And somewhere in between these two classes of materials are also semiconductors. So semiconductors are kind of from name, you already feel that they are neither conductors nor insulators, and they possess quite unique properties. They become conductors when you heat them up, increase temperature, and that results in unique behavior of these materials, which is used to create modern electronic, optoelectronic devices, which are now define our digital world. So these are three classes of materials with different properties. But regardless the fact that materials, in terms of electrical properties, let's say, possess very different characteristics, all of them are made from some smallest building blocks. So what are their smallest building blocks of matter? So if we consider from chemical point of view, these are molecules because molecules define chemical behavior, chemical properties of materials. However, if we go further, molecules consist of atoms. So we can claim that all materials, like all matter, which surrounds us, and ourselves also, we all are made from these building blocks atoms. So let us consider in more details these atoms. So it was figured out that atoms actually consist also from other so-called elementary particles. And we have electrons, which are orbiting the central core of the atom. And this core of the atom consists two types of elementary particles, protons and neutrons. So with neutrons, everything is kind of boring because from their name you can already make a conclusion that they do not possess any electric charge. So they are neutral. However, electrons and protons do have electric charges. They are different signs. So proton is positively charged, electron is negatively charged, and equal in magnitude. So the charge of electron, who remembers what is number of electric charge in coulombs of an electron?
1.6 multiplied by 10 in the power of -19.
Minus 19 coulomb, exactly. So we have this elementary charge, we cannot split it in smaller charges. So that is the smallest charge which exists in nature, and all other charges, electrical, like electrostatic charges, or charges which are transported in electric wires, they will be defined by the sum of some system of these electrons, and that's the main source of electric charge we are going to work with. So now, the key requirement for such a structure is electrical neutrality. And that is translated also to from like this micro world, macro world. So usually under normal conditions, regardless what we consider a building block of matter or some macro object made of some certain material, in both cases, under normal conditions, they should be electrically neutral. Means that the sum of total negative electric charge of all these electrons should be equal to the sum of positive electric charges concentrated in the nuclei of the atom. If a single building block is is electrically neutral, then the material or object which is made from this electrically neutral building blocks will be also electrically neutral. So that is the key requirement, because otherwise, if we would not have electrical neutrality, that would be a complete mess, and all bodies and objects would be electrically charged by definition. So that's definitely not what is happening in nature. However, as we mentioned while talking about drops in clouds, like storm clouds, because of the friction between water and air, there is a chance that some of these electrons will be separated in different environments. So it means that it works not only with water and air, but also other materials. So if we take two different materials, let's say some silk and glass, and put them in contact with some friction between them, there is a chance that some of these electrons will be distributed. So in this case, we charge silk negatively and the glass stick is charged positive. What does it mean in terms of processes which are happening on this micro scale?
Electrons are escaping glass rod.
Electrons are transferred from glass rod to the silk, and then we have electrically charged object. So further, it is possible to make some quantitative analysis of interaction between electric charges. So if we have so-called torque scale, we mentioned about torque scale during previous semester when we described experiments from Sir Cavendish, who measured gravitational force. So in order to measure very weak interactions, it is quite useful to use such torque scale because it requires very little torque in order to measure some deflection of the equilibrium condition for this scale. And then that means we have very high accuracy and can measure very weak forces. So in this case, if we already have negative electric charge on this stick attached to the torque scale and put closer positively charged stick, we observe that there is some attraction between these two objects. So we make a conclusion that when the signs of electric charges are opposite, there is attraction between them. So if we put together two sticks which carry negative charges, then we see some repulsion force, and that is because we deal with the same sign of electric charges. If we have here two positive charges, they will also repulse from each other. So at this point, we know that we have this principle of electrical neutrality. In micro and macro scale, we know that under normal conditions, electric charges should be compensated, positive and negative. Eventually, as a whole system, its net electric charge should be equal to zero. And there is certain interaction from electrical force, which results, which is exerted on electrically charged bodies, and its direction, either attraction or repulsion, will be defined by the sign of these electrical charges. For the same electrical charges, they repulse. For opposite electrical charges, in sign, they attract. I'm sure you did something like this, so you can do it even now if you don't believe that it works. So if you charge some stick, so it could be some plastic pen, for instance, by rubbing your hair, then you can attract these very light, small pieces of paper. The trick here is that paper, as opposite to the stick, is not charged. So you can take a piece of electrical neutral paper, charge this electric stick, put the stick close to the piece of paper, and it will be attracted. Looks like, according to our previous slide, that both of these objects, in the stick and the piece of paper, should be charged, and they should possess different opposite signs of electrical charges in order to attract to each other. However, we have a situation when we have only stick charged and piece of paper is not charged. So, any suggestions how we explain this situation? Why this actually happened, this attraction?
The negative charges on the stick, they repel the negative charges on the paper, and the paper becomes positively charged.
No, not so easy. This paper is not in friction with any other material, so it doesn't have a chance to transfer its electrons somewhere. So by just putting this stick, electrically charged stick, we cannot force electrons from pieces of paper to be transferred somewhere and, in other words, charge the piece of paper. What's actually happening here? We have so-called polarization. So you started correctly. Indeed, if we put this negatively charged stick close to a piece of paper, the negative charges in the paper will be repelled. And in very thin, so of course this is some illustration, But in real life, in very thin surface layer of this paper, you will have a bit more positive charges than negative, because negative charges will be pushed away from the surface of the paper. Such a configuration means that here between stick and the paper, we will have attraction, and it will be larger attraction than repulsion between negative charges here, because the distance here is larger than here. So it means that we create so-called dipole because of polarization of this piece of paper. It still remains electrically neutral. However, due to redistribution of electric charges within the piece of paper, we get stronger attraction than repulsion. And that is enough, this weak difference between attraction and repulsion is enough to compensate weight of these very light pieces of paper and attract actually it to the surface of the stick. So now we gave some general introduction to electrical processes, defined that it actually has to do with electrical charges, which in their turn are like some scalar quantities which define how much electric charges or objects which are carrying electric charges interact with themselves. And we are coming to the point when it's necessary to introduce the Coulomb law, which gives us quantitative description between the of the force, electrical force, which is exerted on electrical charges placed at certain distance between themselves. So let us come to close this presentation. Oops. What's going on? Experimental observations have shown that the magnitude of electrical force, F, let me make it thicker, magnitude of electrical force is equal to some Ke, which is electrical constant, times absolute value of first electric charge and absolute value of second electric charge. So electric force is proportional to the product of electrical charges which are interacting with each other, and reversely proportional to the square of the distance between these two charges. So here is radius square. So this electric constant Ke is equal to 1 over 4 pi epsilon naught. And epsilon naught is a universal electric constant, which is defined as permittivity of free space, and it's equal to 8.854 10 to minus 12 Coulomb square Newton meter square. So what is similar for you with some other fundamental equation which describes gravitational interaction. So it is quite similar in terms of the structure. We have the electrical constant. Instead, for gravitational force, we have gravitational constant. Then we have masses of two objects instead of electric charges, and also distance in second power between them. So the units for electric charges, as we already mentioned, they are coulombs. That's coulomb. And coulomb is actually quite large. 1 coulomb is quite a huge electric charge. So we usually in everyday life are dealing with quite small electrical charges. And if we recall that the charge of one electron is 1.6 10 to minus 19 coulomb, then 1 coulomb would result in something 10 to 18 electrons. So that's quite huge change. We usually will operate with nano, micro coulombs, which is 10 to minus 9 or 10 to minus 6 coulomb, so much smaller quantities. So now, as we mentioned earlier, if we have two charges with the same sign, there is some repulsion between them, and so let's be Q1, this is Q2, and according to third law of motion, these forces should be, which are exerted on each other electric charge, should be aligned in opposite directions and possess the same magnitude. So this will be F21, this is F12, and we can write that F12 absolute value of this vector will be equal to F21 absolute value. And in terms of direction, they will be opposite, as I said, according to the third law of motion. If we have different signs, so we have positive and maybe further negative electric charge, then along this line, which connects these two charges, point charges, so the same line here, we will have forces which will attract these charges to each other. So this will be F21 and this one F12. And this ratio, this equation will be valid for both cases, no matter either we have repulsion or attraction. So obviously, if we have a system of electric charges, not just two, then we need to take into account all electric forces exerted on a given electric charge from all neighbors, which have to be considered. And in a vector form, we need to sum up all exerted forces on this given electric charge from neighbors. And as a result, this vector sum will give us the net electric force exerted on a given electric charge. So we can write that it should be defined as sum for all charges around the given charge. So it will be, we will start from I equal 2 because I equal 1 is the given charge, and all forces exerted from these charges on charge number 1. So that will be net electric force exerted on this given charge of our interest. So obviously, we want also to write the Coulomb law in vector form. So that gives us a possibility to deal with the vector, like orientation of electric force, not only its magnitude. So in general form, we can write the following. So F vector already, electric force in vector form can be defined as Ke, electric constant. Here we have Q1 times Q2 over R square, and here we put R unit vector. So unit vector, we define whatever we want to measure. Let's say we want to know electric force exerted on charge 1, Q1, then unit vector R will be oriented in this direction from the charge Q1 towards charge Q2. So it doesn't have any magnitude, it's just unity, it just defines the orientation. And then, of course, you need to take into account here signs of electric charges. Either they are the same, and we have repulsion, or they are different, then this electric force will be attractive force. So now let us consider some example of interaction between two charges. So let us assume that we have two positive charges, maybe let me move further, which are attached to some massless ropes. So one positive charge, another positive charge. Here is the vertical line which goes through the center of this system. And obviously, because of repulsive electric force between these two charges, there will be some deviation from like equilibrium vertical line, and this will be some angles theta. So this will be some distance a from electric charge to the central vertical line. And now, since we consider this system in equilibrium condition, we have certain forces which should be taken into account. So first of all, there is some weight of this electrically charged body, so mg. Then we have electric repulsive force, it will be F electric. And also we have tension in the rope or string, which keeps this electric charge in place. So here is tension. Now we can consider some resultant. Force exerted as a sum of electric force and weight, which is compensated by tension. And this electrically charged object is residing in equilibrium condition because all forces are compensated. So taking this into account, that all forces are compensated, let us consider it in the scope of a system of coordinates x, y. And obviously we will consider projections of these forces on both axes. So let's consider first projection on axis x, resultant force. So here we have tension times sinus theta. So it's this part, you see, projection of tension vector on axis x. So it will be positive because this projection will be in the same direction as axis x. Then second will be our electric force, Fe. Is kind of aligned parallel to axis x, so we don't need to multiply it to any sinus or cosinus. And what it should be equal to? 0. So we have equilibrium conditions. So then we consider also Fy, projection on axis y, and that will be
t times cosinus theta and minus mg. That also will be equal to 0. So from here we can write that t times sinus theta is equal to electrical force and t times cosinus theta is equal to mg. Now the angle theta, which is the deflection from the equilibrium condition, so tangent theta, will be equal to the ratio between electric force Fe and mg. So this is our angle theta, and we have the ratio between the opposite cutted to adjacent cutted. From here, we can write that electrical force is equal to mg times tangent theta. So now, if we assume that tangent theta is known, we also need to define this distance a, distance between the central line and electric charge. So it will be equal to a times L, which is L is the length of the rope. So it will be L times sinus theta. And distance between the electric charges now will be equal to 2a. And that is 2 times L times sinus theta. So if we consider that we don't know electric force, we want to determine what is electric force from knowing the angle theta and all other parameters, we can determine it in different ways. So we know that it's equal to Ke electric constant times Q square, because electric charges are the same, divided by R squared. So that is Coulomb law. From here, we define that Q, electric charge, is equal to square root of electric force times R squared divided by Ke, which is the electric constant. And in our given case, the distance R between electric charges is defined as 2a. So we have square root of Fe times 2a squared divided by Ke. So further, we can substitute the expression for electric force and the distance, so here is R, distance, 2a, into this equation. So we get Q is equal to mg times tangent theta. Then we have 2L times sinus theta square, and that is divided by Ke. So you see now that in the left side we have electric charge, which we cannot measure directly without specialized instruments. However, in the right side of this equation, what do we have? We have weight of the electrically charged objects, like mass, which we can measure with regular scale. Then we have angle theta, which is also easily measurable, and electrical constant, which is known universal constant. So in this case, we can use such a simple system in order to define determine the magnitude of electrical charge which is residing on these two objects. So let us summarize. We introduce the concept of electrical charge as a scalar number which quantifies the interaction between bodies which are electrically charged. We figure out that electrical force will be either repulsive or attractive depending on the sign of electrical charges which are interacting, and introduce in scalar and vector forms the Coulomb law, which allows us to quantify electric force. And in order to do that, we know that electric force is proportional to the magnitude of electric charges and reversely proportional to the distance between them in second power. So next lecture we will introduce the concept of electrical field, which is the medium via which electrical interactions are happening, and we will meet on Friday. So thank you very much for attention. See you on Friday.